Hey everybody, I thought I'd make another video like this since it's been a while. Um, I do hope those of you with the AP exams did well on the ones this week and that you're studying for, rather prioritizing studying for the ones this week before you start worrying about any of this work. And if you're watching this video after you've already taken them, then I hope that you did well on them. Um, Surely you've noticed that I left you a presentation on modern physics, the topic we started with Albert Einstein last week. This, like I promised, is a topic where we're not going to worry about equations or problem solving, not even any term maps. But I still think it's nice to learn about some of the more modern physics, especially with what you did last week, just learning about Albert Einstein as a person, his life. He's the most well-known scientist in the world, but not many people actually know who he was. They just know some of the work he did. We're going to continue with that vein of taking Albert Einstein and then now analyzing, or rather, trying to understand a little bit about what his work means in terms of the new physics it opens up. Um, you can see the time in the of this video. I won't take more than a few minutes of your time now. So here's a little bit about modern physics. One of the biggest ideas behind this branch of physics is the dual nature of matter, um, and uh, and energy. Dual nature meaning it's got wave and particle properties. So let's just take this from the top. I'll have you just think about some of the wave properties we talked about a few months ago. In fact, we were just wrapping up waves when we started this learning online. You might remember we did the Slinky demonstration in the hallway. We took a look at some lasers refracting through glass. We did a little bit of sound with the tuning forks in the pipes. These were all experiments in our wave topic. So you might remember uh, some of the ideas we talked about in that topic: wave frequency, wavelength, speed, amplitude, diffraction, wave interference, the Doppler effect. Again, these are should be ringing bells in your head. We've already talked about this stuff within our waves topic. Um, and so we could then say, all right, well, yeah, this is all wave business. We talked about this in physics class. Um, this wave model describes many more wave properties than the ones we've talked about. And light also demonstrates all of these properties. So light's a wave. Okay, and here's some pictures that you might remember seeing from our topic. But actually, no, light is not a wave because it does show some, rather, there are some experiments that can be done to show that light does not exhibit wave properties. So sorry if I um, convinced you that light was a wave before. It's actually not really. Let's go back and talk about the photoelectric effect that Einstein discovered in 1905. So um, I mentioned light shows us some properties that mark it as something other than a wave. There are some experiments that scientists had done, even a little bit before Einstein, that shows that light is able to transfer kinetic energy and momentum. These are properties that a particle with mass has. A mass has energy. Mass can impart momentum onto something. Um, so if light's doing that, surely it has to have some sort of particle-like properties. So Einstein thinks about this, and he actually used Max Planck's quantum equations to figure out that, or rather, he could prove that light has the ability to bump electrons to different energy levels and maybe even be emitted if it has enough frequency or enough energy. He actually wins a Nobel Prize for what he calls the photoelectric effect. That's a big misconception a lot of people have. Most people are familiar with Einstein for E equals mc squared or his relativity theories, but he won the Nobel Prize for neither of those. It was the photoelectric effect for which he won the Nobel Prize. That's all I'm going to tell you today. There is a video here, a little cartoon video briefly describing this photoelectric effect. And then there's another video in this presentation about a demonstration of the photoelectric effect with a simple electroscope, which is a device that will just move if it feels an electric charge. I'll let you watch these two videos on your own, and you can try exit ticket number 1. That's linked in the outline, as well as you can in your Google Classroom. I'll see you in the next video. Take care, and good luck if you're taking an AP exam soon. Bye-bye.